final part here, we're going to be talking about solubility effects and Lewis acids and bases. So we're going to start off with solubility effects, where essentially with the solubility effects, we're going to be talking about the common ion again, and this would be a common ion between a soluble salt and an insoluble salt, that yields a change in the solubility of the insoluble substance. Right. So essentially what this means, it's kind of like if I add this much of a soluble salt ion to my insoluble salt, will I be able to form a precipitate, kind of, sort of. Like it's just, do I have enough of this to overcome the KSP for it to actually precipitate? Yeah. So we're going to do an example problem just because I think that's an easier way of explaining this, because it is kind of funky. So let's take, for instance, that the KSP of silver bromide is 7.7 times 10 to the negative 13. And then we have a solution contains a concentration of 1.2 times 10 to the negative 6 molar of silver ions. So then, what is the max concentration of bromide ions that can be added before a precipitate is formed? So we're dealing with a common ion here where we have the 1.6 of silver ions already in solution of AgBr, which is silver bromide. So then we have silver bromide solid, breaks apart into our silver ion and our bromide ion, so that our KSP is equal to Ag Br minus, right? So then we're given our KSP, which is 7.7 times 10 to the negative 13, and we're given a concentration of silver ions, which is 1.2 times 10 to the negative 6, and we're trying to find how many bromide ions we can have before a precipitate is formed. So that basically means that for a precipitate, oh my god, to be formed, it would have to mean that we would have to have enough bromide ions that we would have a number larger than our KSP, because if we have a number bigger than our KSP, that means that it's going to shift to the left. Yeah, left. Well, it's going to shift to the reactants, which is just going to mean that we are going to form a precipitate. So if we want this to be before a precipitate is formed, it's going to have to be exactly at the KSP. So we're just going to solve for Br. So we're going to do divided by 1.2 times 10 to the negative 6, 2 times 10 to the negative 6. So that would give us the concentration of bromide would be 6.42 times 10 to the negative 7 molar before the precipitate would actually form, because right now we're at equal with our KSP, so there's no shift in our expression, so no precipitate has been formed yet. But if I wanted to say, like, how much bromide do I need for the precipitate to form, you would just have to give me a number larger than this, and that would be your precipitate to form. And if I didn't want it to form, it would be a number less than this, so that we wouldn't have a precipitate yet, because we haven't overcome our KSP yet, we haven't dissociated. So, yeah. So then another problem that we can do with the common ion, cool, is essentially we're going to find a molar mass again. So this is another example where it's to find the molar solubility of silver bromide, which is, again, AgBr, in a 3.7 times 10 to the negative 2 molar concentration of silver nitrate. And then we have that the KSP of silver bromide is equal to 5.35 times 10 to the negative 13. So this is the whole common ion thing again. And the first thing that we're going to do is with our silver nitrate, that is a completely soluble salt. So we're going to have a full arrow coming this way for our silver ion and our nitrate ion. That should be a minus. So then initially we're going to have our 3.7 times 10 to the negative 2, 0, 0. And then our change is going to be 3.7 times 10 to the negative 2. And I'm just going to put it in between here because it's the same thing, because it's a 1 to 1. 10 to the negative 2. So that finally this is at 0, and these are both 3.7 times 10 to the negative 2. And this would be our step 1. So then step 2 is that we write our formula for AgBr, which is silver bromide. This is our double arrows. This turns into Ag plus Br minus. And then we do another ice table, but like I said, since this is a solid, it's not going to matter for our KSP expression because we don't even plug it in for the reactants, right? So then our Ag, we're going to start off with the 3.7 times 10 to the negative 2 from the silver nitrate that we just did. And then Br is still going to be 0. We're going to have a plus x, so that we have 3.7 times 10 to the negative 2 plus x, and just x at final. So then step number 3, which I'm going to do up here because I don't know if I have enough room down there, we're basically going to write our KSP expression, which is our silver times our bromide. And we know that the KSP for silver bromide is 5.35 times 10 to the negative 13, which is going to be equal to 3.7 times 10 to the negative 2, that's a 13, I forgot my 1, plus x times x. So then in this case, it's the same thing as other equilibriums. This number is so small that we can basically ignore this plus x, like that's gone. So then all we have to do is solve for x, and to do that we would divide by 3.7 times 10 to the negative 2, so that our concentration of Br, which is a 1-to-1 ratio, so it's going to be equal to our concentration of Ag, is equal to 1.45 times 10 to the negative 11. So then finally, to find the molar solubility, again, we just use our molar ratio. So if we have 1.45 times 10 to the negative 11 moles of Br all over 1 liter. In 1 mole of Br, we create 1 mole of silver bromide. So therefore, our molar solubility of silver bromide is 1.45 times 10 to the negative 11 moles over liters of silver bromide. So yeah, this is essentially what the common ion effect does. It's just that you now start off with this thing again, and then you just plug it in to solve for your concentrations or whatever your problem's asking you for. So it's not too rough. But I also realized that I forgot to do a practice problem like this in the other video. So we're going to do another KSP one. So, oh my god, where's our mouse? Okay, let's do this as example 2. This should be example 3, but okay. So we have that the KSP of magnesium hydroxide is equal to 4 times 10 to the negative 17. And we're trying to find the solubility of our magnesium ion. Yeah. So our first step is that we're going to do our expression, which is magnesium hydroxide breaks apart into magnesium ions plus 2 hydroxide ions because we're balancing, right? I forgot to put my solids in aqueous. I keep forgetting to do that, but you guys know they're there. So we're going to do our ice table here just so that we can see what our values would be, and these don't matter for our KSP expression because, like I said, it's the solid. So then we still have 0, 0. A change is x. The change here is 2x, so we have x and 2x, right? So step 1. Step 2 is writing our KSP expression. That's too many noises together, the alliteration, oh boy. Which is just going to be magnesium times OH squared. And then we're going to actually plug in for it. So we're going to have the KSP, which was 4 times 10 to the negative 17, is equal to our magnesium concentration, which is x, times our hydroxide concentration, which is 2x squared. And we're just plugging in these values into it. So we're going to simplify this to have 4 times 10 to the negative 17 is equal to x times 4x squared. And it's like that because we distribute this exponent to everything inside of here. So we have the 4x squared. So we have 4 times 10 to the negative 17 is equal to 4x cubed. And we divide everything by 4. So I'm going to move up here, like just right next to it, so that you guys can see what I'm doing. So then, if you divide that by 4, you end up with 1 times 10 to the negative 17 is equal to x cubed. And you take the cubed root of this, and you should end up with 2.15 times 10 to the negative 6 is equal to x. And in your calculator, if you guys don't know how to do the cubed root for it, and because we all have different calculators, I think, it's the exact same thing as if you were to do 1 times 10 to the negative 17 raised to the 1/3, because this just means power over root. So it's to the power of 1 to the third, to the cubed root. So yeah, that's just, these are the same thing. Right. So then let's move on to step number 4, which is that now we have the concentration, which is this one. So our concentration of magnesium 2+ is equal to 2.15 times 10 to the negative 6 moles per 1 liter. And we're going to convert that into our into our solubility, which is grams over liter, by just doing 1 mole of magnesium ion gives me 24.3 grams, which is equal to 5.24 times 10 to the negative 5 grams per liter of magnesium. And that's the answer for that problem. And the reason why I did that was just to show you guys that if you have a difference in our 1-to-1 ratio, you need to put that 2 into the concentration and square it also, or else you're going to get your values wrong, which is going to mess up if you're trying to find molar solubility or solubility, because you're going to have the wrong X value. So yeah, that's the reason why I brought up that problem. So then the next concept that we would go over with with solubility effects would essentially just be kind of how solubility affects, how pH affects solubility. Yeah, so let me just write solubility and pH. And essentially what's happening here is that if you were to have insoluble hydroxides, because mostly everything with a hydroxide is insoluble, or just anything in general that's insoluble, it's affected by your acidic or basic environment. So, okay, insoluble OH. So if you were to put it in an acidic environment, which means it has H pluses floating around, right? So because of those H pluses floating around, plus your OH minus, you're going to form water. Like, that's just what happens. And because of that, your solubility will increase. Whereas if it was in a basic environment, you just have OHs. Because you just have OH and OHs, and they're both minus and exactly the same, they're going to repel each other. So you're not going to form water, nothing's going to happen, they're not going to want to interact. So your solubility would decrease. And that's essentially what the solubility in pH does. It's just in an acidic environment, your solubility would increase. In a basic environment, your solubility decreases. So yeah, not much to it. And then there's a final thing that has to do with solubility effects, which is known as fractional precipitation. Which essentially what this means is that you would have the gradual addition of like one substance to another. So it's kind of like a titration. Yeah, so like you're trying to form a precipitate instead of a neutralization in this case, which it just means that you may have 2 or more different ions. And it's basically that you have 2 ions with different KAs. KSPs. So because of these different KSPs, you're not going to know which one would precipitate first, like just by looking at them, but with the KSPs you can, because it's essentially that the lower KSP value will precipitate first. And that's the bare bones of the fractional precipitation. It's just 2 or more ions with different KSPs, and the lower KSP value will precipitate first. So yeah, that's just kind of a conceptual thing for you guys to know, because I know it comes up in your homework, I think. So that's pretty much all I'm saying for these things.